Okay, so we are now going to talk about two important sorting algorithms. One is a merge sort. So merge sort in one sense is sort of opposite of heap sort, in the sense that the heap sort is really clumsy for linked list, but very good for arrays. So heap sort is clumsy for linked list, but good for arrays. Merge sort, on the other hand, is actually good for linked list. Good in the sense that we can actually get an in-place sorting algorithm. But the sorting algorithm for arrays is non-in-place for arrays. Okay, so we're going to look into merge sort because as a technique in general, it is great for linked list. So if someone gives you a problem of performing a sorting operation, an in-place sorting operation for linked list, a good algorithm of choice would be merge sort. Now, merge sort is a divide and conquer strategy. So this is divide and conquer. And likewise, the quick sort is also a recursive divide and conquer strategy. But quick sort is the best known comparison-based sorting algorithm. I'm calling out comparison-based sorting because you just saw how counting sort can be really very fast sort, but it is not generally applicable. But if you are taking any comparison-based sorting, then quick sort is the best possible known algorithm. So we're going to therefore discuss quick sort. All right. So now let's just develop a general. So this is also kind of based on divide and conquer recursive strategy. So now let's just talk in general. Like if you were to approach the sorting in a general fashion, how would we approach it in a divide and conquer style? So we would choose for a base case, right? So first we will say that, okay, I want to sort a list L, right? That can be a linked list or array, but I have a list. So the base case would be if you have only one element. Let me just, so this is a list of length n. So if you have only one element, then the sorted list is simply going to be the list itself, which is only one element. So this is the base case. And the inductive step or recursive step is going to be the interesting strategy. Depending on the strategy we adopt here, is going to fall in the category of merge sort or the quick sort. So the inductive strategy, one strategy that you can think of is that I just simply split my list L into two non-empty lists. Okay, call them L1 and L2. Okay. So then after I have split L into two non-empty lists, then what do I do? Then I would like to sort L1. Okay. And I store that sorted entry in, let's say, L1 dash. And I would like to sort L2 and store in another list called L2 dash. And then after I got two sorted lists, then all I need to do is just merge them together. So L dash is going to be the merge operation of L1 dash and L2 dash. So if you recall, in terms of the recursive strategy, so this is our essentially decomposition operation, right? And this is our recomposition operation. And then we are done. So now if you have to now express this in terms of an algorithm, how would it look like? So I would write merge. I have got an array, let's say A. So typically when we are sorting in a divide and conquer strategy, it would be good to identify the start and the end point. So if you remember, even in the binary search case, we have an array and we have a start and an end. So this is the index to the start and the end element. So I and j. So what do I do? So applying this strategy. So this is MergeSort algorithm, which is essentially following this recursive decomposition and recomposition strategy that I just listed down up. So if somehow or other I find that I is greater than equal to j, then I need to return. So this is our sort of base case, right? So if you have only one element and you have I and j pointing to the same, then you just return. And another possibility that can happen, which is very similar to the binary search situation, that these two can get swapped. So I becomes here and j comes here, you know. So as a part of the recursive strategy, so this can happen. And therefore, we are putting the condition as greater than or equal to j. So I is greater than equal to j, which either represents this singular element situation, or in the process of doing the progressive breakdown, you may give a range in which the I and j can get swapped. All right. So I and j can get swapped in the sense that that I can become actually greater than j. So otherwise, what do we do? So we apply some sort of splitting. So we did not talk about what kind of splitting we would like to make here. We're just saying divide into two non-empty lists, L1 and L2, because we were trying to generalize the sorting. So when it comes to merge sort, so just like binary search, it tries to break in the middle. So when the splitting strategy is that this is the split in the middle, then this becomes essentially a merge sort algorithm. So if you have to break it down in the middle, so what do we have to do? We have to find mid index, which is going to be equal to I plus j divided by 2. This is very similar to the step that we take in binary search. Okay. So now we have got two pieces, right? If you have this array, we got the central piece, which is the mid. And here you have got I, here you've got J. Because here we are storing the entry. So let me not write down I and J here, but let's say I points here and J points here, okay? The index. So what should I write down for merge sort, this recursive call? So I can write down A here, but what should be the range here? So what are we sorting here?
Mid -1.
Correct. So we can go from I. So in this case, remember, we have to include mid somewhere, right? So suppose you include mid on the left half, then this guy starts with mid plus 1, right? Because you cannot leave out mid. You have to include the mid. So it's going to be I to mid, okay? And likewise, this merge sort, here it's going to be A from, now you can clearly see that it is going to be mid plus 1 to J, right? So now what's going to happen after calling merge sort on this piece and this piece? You will have the sorted list, right? So after you get the sorted list, then you have to somehow merge these two together, right? After it has been sorted. So I would need to perform a merge. So notice that I do not need to necessarily do anything but pass the same thing, which is A. Why? Because from I and J, I should be able to locate the mid. That's not a problem, right? So I will continue to pass I and J, and that is sufficient actually. I don't need to even pass mid, because mid is simply I plus J divided by 2, which I can do. Is that clear? So the whole complexity right now is how we are taking two sorted lists and actually merging them together. So what would be the strategy for merging? And that's where the complexity for the merge sort algorithm comes in. So
I have a question.
Go ahead.
Sorry, could you clarify the last merge line? Could you not do, for example, merge sort, like the first two lines, right? Could you not do merge sort first part plus merge sort second part?
You mean concatenate?
Yeah.
Okay, so just think that what's going to happen, because you have no control over this range of data, right? You could have 2, 3, 5, 7. Sorry, I'm writing in the sorted order. 8, right? 6, 4, right? 2, right? So when you want to split, you just got an arbitrary split here, right? So after sorting, you will get 2, 3, 5, 8. After sorting here, you get 2, 4, 6, 7. So if you concatenate, it's not going to solve your problem. So you have to merge the two sorted list. So you expect 2, 2, then 3, then 4. So this is the effect of merging two sorted list. That makes sense?
Okay, yeah. Then like, wouldn't it be just like a small detail? Wouldn't it be merge sort AIJ, not merge for the line, the third line?
Third line
Below.
it has to be mid, right?
No, sorry. I meant, below the second merge sort line, wouldn't it be not merge A, comma I, comma J, but merge sort?
Comma merge sort.
I'm saying like when you call the function merge,
Yeah.
right? Like I thought we're calling merge sort, not like merge.
So this is the recursive call, right? So this is the one that is doing the sorting of the individual pieces, correct? Merge,
Yes. Uh-huh.
merge is taking these two sorted lists, right? Because as a result of this merge sort call, what has happened is that we have sorted this guy, right? As a result of calling the second merge sort,
Mhm.
we have sorted this guy, correct? The last step is basically taking these two
Mhm.
lists and merging them together.
Okay.
Is that
Makes
clear?
sense. Yeah. Wait, wouldn't you have to sort it again though? Like you can't just, like we said, we can't just concatenate it. Don't you have to
You cannot
merge sort
concatenate,
it
but this
again? Like from
this merge has to take care of preserving the sorted order. It's not just a arbitrary merging, right? So this preserves the sorted order. Is that clear?
okay.
Yeah. So we're going to see how merge is going to happen. Okay. Okay. So let's write down the algorithm for merge now. So the point that is going to come through is that in order to merge, you're not able to maintain the in place ability. That's the key. You would need an auxiliary storage to get the sorted order done. So overall, you can see, like, if you take this example, right? So 2, 3, 5, 8, right? We need to merge with, so we are taking this list and taking this list, 2, 4, 6, 7. So what's going to happen is that it's going to go and keep moving forward the pointer on this particular list. And likewise, it's going to keep moving forward the pointer on this list. So depending on which one is smaller, it's going to keep placing inside the auxiliary array. Okay, so first it will encounter 2 and 2 because the pointer to begin with is here, right? So it sees 2 and 2. So if it has to pick, it can pick any. So it picks 2, right? So once it picks 2, then the pointer moves forward, goes to this. Okay, then now it compares 2 and 3. So 2 is smaller than 3. So 2 gets chosen again. This 2 gets chosen. Now, having chosen this 2, now the pointer can move forward. So now the next comparison between 3 and 4. So 3 is smaller. So 3 gets chosen. And then the pointer moves forward. So now the comparison is between 4 and 5. So 4 is smaller. So 4 gets chosen. And the pointer moves forward. Next comparison is between 5 and 6. So 5 gets chosen, the pointer moves forward. Then 6 and 8, then 6 gets chosen, the pointer moves forward. And then between 7 and 8, 7 gets chosen. And whichever list remains empty, I mean, it may so happen that this has even more entries, 8 and followed by 10, for example. So these are yet to be kind of finished. So it just appends whatever is remaining. So it's 8 followed by 10. And this is how you get the merged entry. Okay, so there's the overall process. Now we're going to see it in action. I mean, see it in action in terms of the algorithm. So our signature for the merge function is that we are passing in A, and then you have I, and then J. So the first part is you initialize. So what do you initialize? You have, let's say, some start is equal to I, and then you have the mid. You have to calculate the mid. That is going to be I plus j divided by 2. Okay. And then you have k equal to mid plus 1 and L is equal to I. Okay. So what did we do here? We essentially divided it um, into two pieces, like one which starts at mid plus 1. So k is going to begin here. So this is our k because this is mid plus 1, right? And then start is here. So this is our start. So k is here, the start is here, and L is also pointing to the same start node. So L is going to advance forward, okay, and it's going to cover this set of nodes, and then k is going to advance forward and it's going to cover the second set of nodes. So that's the basic idea. So this is the key initialization step. So you can see in this picture. So now here, this is our k. Sorry. This is the first list. So this is our L and this is our k. Okay. Which is essentially mid plus 1. Okay. Now we run a while loop. So while I is less than equal to mid. Okay. And k is less than equal to j. So you want L to go from I to mid, right? And you want k to go until j, right? So that's why you have set this up. And then you have if a of L, okay, is less than equal to a of k. Sorry. Then what do? You have an auxiliary storage, let's say B, okay? You go B, okay. Let's do this way. Sorry. Let's keep this I. So let's keep this I. So this L as well as I is here, right? So we are keeping this I. The reason is that we want to use L for our auxiliary storage. So we can say L plus plus equal to A I plus plus. Else, so basically what we did is we compared. So this is AI and this is AK, right? If we find that AI is less than equal to that, then we are storing into the auxiliary. So this is our B, which is in formation, the merge list. So it is picking the lower entry, and at the same time, it is incrementing the one which is the lower one, the lower value. So it is incrementing L to populate this B, and it is also incrementing the corresponding I or K, whichever is making the difference. Okay. So now if it's other way around, where AK is greater than less than equal to AI or less than AI, then it's going to choose the element from here, and it's going to increment K forward, right? So it's going to be B L plus plus equal to A of K plus plus. Okay. And then you're done. So as I said, now it may happen that one of them are still needing to be appended to the end. So therefore, we need to perform this operation. So if I happens to be greater than the mid, okay, then what do we do? For K, today my pen is not cooperating at all. K less than equal to J, you keep doing B L plus plus equal to A K plus plus. Else you have for semicolon I less than equal to mid. So this is kind of the remaining entries. You just feed that in. So L plus plus equal to A I plus plus. Okay, so this portion is the copy the remaining entries. Okay, and this portion was the merge operation. Okay, any question? And this portion you can say is the setup or initialize. And we can close the bracket for the merge function. Okay, so now the question is, what is the complexity of this algorithm? How would we evaluate the complexity of this algorithm? So one is that we can take the recursive formulation, and you can express T of n is equal to T of n by 2, because it is splitting into two parts, plus order of n for merging the two lists. And then you can solve the recurrence relationship. Another way of looking at it could be, if I have the numbers 0, 1, 3, 4, 5, 7, 8, 9, let's say, and then I split into 3, 5, 7, 9, and then 0, 1, 4, 8. Keep splitting 3. So I split 3, 7 and 5, 9, 4, 8, and then 0, 1. And then I have got 3, 7, and then 5, 9, then 4, 8, 0, 1. So the way to see it is that I 7, 3, 9, 5, 8, 4, 7, 0. So the merge sort is happening in this direction. This is my input. Okay, you might be wondering what's going on. So we kind of after dividing effectively, if you want to see what happened is that we first merged this, right? And then we merged these two, and then we merged these big ones back to the sorted one. So this is our output, and this is our input. Okay, the reason we are showing it this way is that if you see the overall number of levels here is going to be, because you are giving a split, right? If this is your n, right? This is your n. This is going to be order of log of n. So therefore, the overall complexity you can see is going to be order of n times log of n. So this is one of the ways of looking at it just visually. But another way of approaching that I'm going to leave as an exercise for you, which we can do later on together. But at this time, this is the recurrence relationship. And we can see that T of, if you have only one element, then it's going to be order of 1. So with the combination of this, if you can take this as an exercise to show that if you solve this recurrence relationship, you will get order of n log n. Any question?
Wait, so just to clarify,
Yeah.
we do the merge sort, right?
Yeah.
So when we're splitting the unsorted list, we're basically recursively splitting until we compare like two numbers. And then we recursively, like add the two numbers together, which makes like a bigger, in this example, array with 4, and then we merge that again. Is that kind of the idea?
Right. Yeah. So this was you can see the recombination step happening, right? This is the merge part. This is merge. So at the lowest level, it's just single element, right? You merge here, and then finally you give a merge here.
And could you have not gone from, like, for example, the initial array, right? So 7395 8410. Could you have not gone from there directly to 3579 by splitting it into like two larger arrays? Like, why is that middle step necessary?
This step?
If that makes sense.
Which
No, the step where you break it into two numbers.
Yeah, maybe I confused you by writing it that way. I was just trying to write it so that you can see the complexity come through. If you want to see this in action, it would look like this, you know. So first split will happen like this: 7, 3, 9, 5, right? And 8, 4, 1, 0, correct? Then the split will happen further: 7, 3, 9, 5, 8, 4, 1, 0, right? Then 7 and 3, 9 and 5, 8 and 4, 1 and 0. This is how we generally show the recursion, right? So then we are merging, right? We take this and this, right? So when we merge here, right? Then by merging, we get not 7, 3, we get 3, 7. By merging, we get 5, 9, right? By merging, we get 4, 8. By merging, we get 0, 1, correct? And then when we are merging these two back,
Yeah.
right? Then we are composing essentially what comes out from here as a result of merging is going to be 3, 5, 7, 9, like that, right? So I was just showing here in a reverse way just so that I could write down these, the total number of operations involved and the total number of entries here. So you can just see it's just n log n when you see this one. Is that clear, Chris?
Yeah, thank you very much.
Okay. I need to connect my charger. Okay. Okay, so I think just an important point that I would just wanted to clarify, or not clarify, but reiterate, and that is that the natural sorting algorithm for linked list is MergeSort, but not an in-place sort for arrays. Okay. So this concludes our discussion on MergeSort. Now we'll just